The organizers for inviting me. Okay, so let me start. As always, I start with a flower. So this is star magnolia, Magnolia stellata in Latin. And maybe here it's not known because it's I think the most frost-resistant magnolia.
I have one.
Oh, okay, good. But you don't live in Alabama.
Yes.
You do, and you have magnolia. Okay, great. So it is frost-resistant. So this picture I took last year, and last year we had terrible frosts. So. This is a nice picture of a flower. Now, if you zoom out, which I cannot do because it's just a still picture, you will see that there is a big bush with just one flower. Okay. So now, this is my co-author, Sonia Stimac, which many of you know very well. And she, in fact, a year ago at this conference, she was giving a short talk about lossy-like maps, but rather technical. I will try to do some more general thing, and I will be talking about two papers that we wrote, and we wrote them in the wrong order. So I will be kind of switching, starting with the second one about lossy-like maps. So what are lossy maps? So the second, can I use this? So this is the formula for anon maps. And these are very well-known maps. So somewhere in the 60s, I think, Michał and just by 60s, maybe it was early 70s, was experimenting with handheld calculator, not computer yet, to find some simple formula which produces some nice attractor. So attractor is so you. As in the, I understand that everybody here knows what a dynamical system is. We have a compact space, and which is mapped to itself by a continuous map. We iterate this map, and an attractor is the set such that it attracts maybe all points, maybe at least some points from the neighborhood. So here it's a map of a plane to itself. Plane is not compact, but for some values of parameter, for anon it's 1.4 and 0.3, the standard values, but of course you can take other values. So he observed that there is some set homeomorphic to a disk. In fact, it's some quadrilateral, which is mapped to itself, and when you make those numerical computations, you get a nice picture of an attractor. And then for many, many years, people wanted to prove that such a thing really exists, because when you make numerical experiments of this type, so you take one starting point, iterate the map, and then iterate and start plotting, and you see definitely some attractor. But what if it's not an attractor which is let's say a continuum, but if it is just a periodic orbit, attracting periodic orbit of period 10 to the power 300? Okay? You cannot see it. You cannot distinguish it from real attractor which is connected. So finally at some moment Benedicts and Carleson showed that if A is small, then there is a set of parameters of positive Lebesgue measure for which the attractor, the strange attractor, exists. Okay, but at that moment nobody knew it yet, but there was a guy called René Lozi who invented such an attractor. So what did he do? He used the same formula, but instead x squared, he took absolute value of x. And now, because there is a book about Lozi attractor, we know the full history. In fact, I play some role in the history. So these are excerpts. No, this is the Lozi attractor for 1.7 and 0.5. So you see that this is some continuum which is very similar to inverse limit of, say, interval map. Okay, this is history. So these are excerpts from the book, just pictures from the pages of the book. So the book is Lozi Mapping Theory and Applications by Zerulia El-Hajj. So, as you see, it is known when this attractor was invented, when this map was invented. It was June 15th, 1977, around 11 a.m. And as if you read this, you see the department was small and everybody had to attend the presentation of some PhD thesis, although maybe you wouldn't understand anything, so you could think about your own things, and the results may be very good. So if any of you gets bored by what I'm saying, please start to do your own thing. But then when you write a paper, please acknowledge. This theorem was proved during a boring talk by Michał Misiurewicz at the 52nd and so on. Okay, so this is one thing. Now some more information. This is not continuation of the slide. This is from different place. So the second thing is that there was a meeting in France. At that moment I was spending 1 year in France, so Michel Henon was there and also René Lozi, and I was there, and Lozi was giving a talk. I got interested, and then if you look at the third quotation from this book, there was the same year, but half a year later, meeting in New York. And at this meeting, already between those two meetings, I made some work and wrote some paper about Lozi maps, and it seems like I was the first one to call this map Lozi map. But it was kind of obvious. If a non-map is a non-map, then this map, which was invented by Lozi, should be Lozi map. Okay, and here he claims that hundreds of articles have been published on this topic in various fields, not only pure mathematics, some applied mathematics, and so on. Okay, and this is the picture from the paper that I presented in New York. By the way, one funny thing that I remember after my talk there was somebody taking shorthand notes, and then I was sent a transcript, and I was talking about a non-map. Okay, so I tried to pronounce the name of Enon in French way. Not Henon, but Enon. So then in the transcript, it was written. Let's see. This way. So, okay. So this is the picture, and this is the picture in the parameter plane. A horizontal and B vertical. And there are various lines which sometimes mean that something bad or good happens in terms of existence of attractor when you cross that line. And some lines are not really that something happens, but that some kind of estimates work or not work depending on which side of the line you are. And here you see such a almost triangle S. Here the tip of this triangle is cut off, and for AB in this triangle, really there exists this strange attractor. And what is really the difference between a non-attractor and lossy attractor? That the map for a non-attractor, the non-map is smooth. So it's differentiable everywhere. For the lossy map, there is, of course, this vertical line, the y-axis, where the map, x equals 0, where the map is not differentiable. So from this point of view, it's much worse. But on the other hand, if you look at the Henon map, then you don't have any kind of special points where the direction is changed. And it's very, very, very difficult to prove for such maps whether we have, say, an attracting periodic orbit of high period, or maybe a strange attractor, or maybe something else. For the lossy map, it's much easier because we just have two linear maps. Those maps are hyperbolic. So one eigenvalue has absolute value larger than one, the other eigenvalue has absolute value smaller than one. And even if you take some random composition of those maps, still you have this hyperbolicity. So you kind of pay something for this nice hyperbolicity, so you lose global smoothness. And basically, so the difference is the same as between the quadratic maps. Okay, this is so f of x equals ax 1 minus x on the interval 0, 1, and the tent maps, which are piecewise linear. And again, studying those maps is much easier than studying those maps. But these are smooth, these are not smooth. Okay. So what about lossy-like maps? In the one-dimensional case, the situation is kind of very simple. I'm thinking about unimodal maps. So there are two pieces of monotonicity. Map is increasing on the first one, decreasing on the second one, and you have basically one parameter. You take your map and you multiply by this parameter A. So here I could write a formula also, but you see what it is. Also you multiply it by the parameter, it goes up and down, but in such a way you get basically all possible topological types of such maps. Maybe not exactly, but basically all of them. So this is a naturally one parameter family. Now for the non-maps or lossy maps, you have two parameters, but naturally maps of this type should have infinitely many parameters. So it's not true that if you find a formula or even not a formula, something. How can you do it without explicit formula? Well, you just make some assumptions and iterate your map, and you get something very similar. Then it's usually not true that this is conjugate to one of those non-maps or lossy maps, because you have only two parameters in infinitely many parameter family. So what we did with Sonia was we introduced some much larger family. Of course, in order to have the same kind of behavior as for lossy maps, we need to make quite strong assumptions. So, first if you speak about hyperbolicity, you can work in two ways. You can think just about the derivative linear map and this unstable, stable directions, so eigenvalues with absolute value larger and smaller than 1, which varies from point to point, but it's much better sometimes to think about cones. So you take the derivative of the map, and then you have two cones. One cone is stable, one cone is unstable. If you take a vector from one cone, then it's stretched. From the unstable cone, it's stretched, but the cone goes to itself. If you take the cone from the stable vector, you go backwards. It's an invertible map. You go backwards, and again, if you go backwards, your vector gets stretched and the cone goes to itself. Okay, so we define the cone. If we want to do it formally, it has to depend on some parameters. So, and the vector v, which is the kind of the axis, and L, if you vary L, it's thinner or wider. Okay, and now you can change your coordinates linearly so that those cones have axes which are horizontal or vertical. That's lemma 1 basically. Now, the point of lemma 2 is that if you have this cone, and if you have some curve in the plane such that the tangent vector to this curve is always in this cone, then this curve is a graph of the function with Lipschitz constant, which you can explicitly compute. Okay, and now once you have this, and once you have two cones. So one cone is this, the other cone is that. If you have two curves, one has the direction, so the tangent vector in this cone, one in that cone. If they are kind of infinite in both directions, then they have to intersect, and they intersect at exactly one point. So this is kind of obvious if you think about it. Okay, so we have our cones, and now we produce a cone field, say in the open set or in the whole plane. So at each point we have a cone, and the cone was given by two things, a vector and a number. So those vectors and those numbers, we assume that they vary continuously with a point. So this is a continuous cone field. And now we make some assumptions. So for the lossy maps, really you have two maps. One you apply in the left half plane, the other you apply in the right half plane. So here we will have also two maps, and we want them to be hyperbolic, but we want them not to be hyperbolic kind of independently. We want also the compositions of those maps to be hyperbolic. So we introduce this notion of synchronously hyperbolic. So they should be both order reversing or both order preserving. And there is this universal pair of cones and cone fields, which those cone fields, the universal cones means that these are just cones, they don't vary with a point. But now we have those not corn fields, that would be Indiana, okay. Cone fields, and at each place our cone from the field is contained in this universal cone. And those maps are hyperbolic. This hyperbolicity is given by those cones. So as I said, in the unstable direction, when you apply your map, you look at the derivative of the map, then it will be stretching in the unstable direction, in the direction inside the unstable cone, and it's not enough to say, you don't say that it's contracting in the stable direction, you say it's stretching in the unstable, in the stable direction when you go backwards. So this is this S2. And then we need some divider to tell us where we use one map, when we use the other map. So S3 says that there is this smooth curve such that on this curve both diffeomorphisms F1 and F2 coincide. And we want this curve to be kind of vertical. So vertical is stable direction. So this cone is stable, this cone is unstable. So it should be in this cone, I mean again the tangent vector at each place, at each point should be in the stable cone. And this divider is infinite in both directions. Okay, we call it divider. So, and we'll refer to the part of the plane to the right of the dividers, the right half plane, and to the left half plane. So we have those two maps, and then we do the obvious thing. We define our map F as the one map in the right half plane, the other map in the left half plane. So this is the generalization of this thing with absolute value of x. And now, when do we call the map lossy-like? So first we have to make some assumptions which makes it similar to what happens for the lossy family of maps. About orientation preserving or orientation reversing. So here we want those maps to be orientation reversing. And we want it also to be contracting. So it will be expanding in one direction, contracting in the other direction, but contraction is stronger. So the determinant will be between -1 and 0, so that's L1. Now, something that unfortunately we have to assume, it would be nice to have some simple general assumptions which imply that, but if we want to make such assumptions without explicitly assuming existence of a tracking region, they would be very complicated and not so general. So we just make such assumption that there exists a tracking region. What is tracking region? Tracking region is a region which is mapped into itself. And in fact, you want a closed set which is mapped into its interior by the map. So there is this tracking region delta, and we assume it's homeomorphic to an open disk, and its closure is homeomorphic to a closed disk. So it's mapped by F into its interior. Now, of course, for the lossy map, for those values of parameters, I showed you such a tracking region exists, and you have to prove it. But here it's assumption. And then we make two additional assumptions. L3, I will show a picture in a moment what that means. And L4 is the stretching factor lambda, which we used in the previous definitions. So in the unstable direction there is stretching. So it should be larger than square root of 2. So maybe I will explain this condition. So if you have some experience with the tent map, you can see that there is a big difference between the situation when the slope is larger than square root of 2 and when the slope is smaller than square root of 2. If the slope is smaller than square root of 2, then you have two intervals such that this goes here, this goes here. This is a cycle of intervals of length 2. If the slope is larger than square root of 2, then you don't have this, and if you take the core of the map, so the interval from the second image of the turning point to the first image of the turning point, then the map on this interval will be transitive. There will be a dense orbit. So Why does this happen? Because when you iterate the map, there is a constant competition between stretching and folding. Okay, here we have for the 10th map folding. For those maps, again, you have folding. So, if the stretching factor is larger than square root of 2, then in 2 steps, you stretch by factor which is larger than 2. If you fold, still the stretching factor is larger than 1. If you fold, you divide the length by 2. And when another thing which is maybe not so obvious, but that's true, that this folding cannot occur 2 times in a row. So you have to wait for 2 iterates for the folding to occur again, and if stretching is larger than square root of 2, then stretching wins. So you get total stretching for 1 dimension, hyperbolicity in 2 dimensions. And of course this is a sufficient condition for, maybe not of course, but for lossy maps or lossy-like maps, it's sufficient condition for that to occur, but not really necessary. Okay, so what does the theorem 1 say? Maybe I will go to the next slide to show what those things mean. So you have this picture. Gamma, this vertical line, is the divider. Now there is a point called x in the right half plane, which is a hyperbolic fixed point, and this kind of horizontal, or not quite horizontal line, but in this curve which is in the unstable cone. And then it goes like that. This is the unstable manifold of x. So these are points which, when you go backwards, are attracted to x. And this line which goes to M, this is a piece of the stable manifold of x. So these are points which, under iterates, get closer and closer to x. Now this kind of horizontal line through everything is f of the gamma, so it's the image of the divider. So what did I assume? L3, that this segment, it's a curve really, part of the unstable manifold of x between f3 of D and f of D intersects xm, which is in the stable manifold. So f of D is this plane. D is the intersection of the first intersection of the unstable manifold of x with the divider. So this line intersects that line. M is the intersection of stable manifold, first intersection with the divider. So this is some technical assumption which is necessary in the proofs. Okay, and what do we get? The first theorem. So suppose, now we apply the name lossy-like if L1 and L2 are satisfied, and those S1 through S4 before. So if it's a lossy map and it also satisfies L3, then the intersection of all images of the tracking region is equal to the closure of the unstable manifold of the fixed point x. And if additionally f satisfies this fourth assumption, so the stretching is sufficiently strong, then on this attractor lambda, this intersection or closure of the unstable manifold, f is topologically mixing. So if you take two open subsets of lambda, of course open in the topology of lambda, because it's nowhere dense in the plane. So if you take two open subsets of lambda, then starting at some m iterates, images of the first set will intersect the second set. Of course, when I say open, I mean open, non-empty. Okay. Some people write open M. Okay, for that. Okay, so now we have our big family of lossy-like maps. And the question is, were we lucky and did we really define something else? Or maybe our definition, which is supposed to give us infinitely many parameters, which of course we cannot find explicitly, but that's the aim. Maybe we got exactly the same family in the sense that every lossy-like map is topologically conjugate, and conjugate in a nice way to the lossy map. Okay, so we try to check it, so we try to find some lossy-like map which looks differently than any lossy map. So we modify the formula by subtracting Cx here. So for C equals 0, this will be just lossy map. And we make three assumptions on A, B, and C. Such simple assumptions which, when you get to the picture which to this picture, really mean that we are in this triangle S even without this small piece cut off. So these are those three lines. That's for C equals 0. Oh, too far. Okay. And then we prove, these are calculations, that those maps are lossy-like, satisfy L3 and L4. And then we take some natural values of the parameter, which you see here. These are, of course, approximate values. And C equals 0.1. And then we compute something which we call needing sequence. I will talk about it in a moment. I still have some time. Okay. And it seems that we get something which does not appear for the family of lossy map. And this is not really a proof, but that's something that you can believe in, because the calculations, as you see, are kind of very precise. If you think about the precision and possible error, then you see, okay, it must be true. And now this is the attractor for this map, and you may see that the place where this kind of line ends, this is two lines really, and this, they are kind of lined up. So the point X is here, and here there is the stable manifold of the fixed point X. So those, we computed those long numbers in such a way that those points are on the stable manifold of the fixed point. Okay, and this is the picture in ABC, how this set where the map is lossy-like and L3 and L4 are satisfied looks. So the blue phase is when C is equal to 0, and then it gets thinner and thinner. Okay, so I was using the name kneading sequence. So this is of course taken from the theory of maps of an interval, where unimodal maps, for example, where you just divide your interval at the turning point or critical point, if you prefer that name, and say this is one piece, this is minus, this is plus. And then you take a point, you look at its trajectory, and you get a code which is a sequence of pluses and minuses. So here we do the same. We have the divider, and there's plus on the right, minus on the left. But the map is invertible, so you can go both ways. So your sequence is by infinite. So this P bar is our kneading sequence and our itinerary of a point, really. And then you do kind of usual things that you do when you work with kneading theories. So you look which sequences you get. So the sequence is admissible if its code corresponds to some point of your attractor lambda. And then you have the symbolic system with two symbols, plus and minus. And you have to prove, okay, you can go one way, which is obvious. You have a point, you look at its trajectory, you get a sequence. But you also have to prove that you can go back. So lemma 4 tells us that for every admissible sequence, there is exactly one point on the attractor with this itinerary. Okay, and then we have to prove that, there is this natural projection now. From sigma lambda is the space of sequences with product topology, of course. This is plus minus 2 power z. So in plus minus, this is 2-point space. You have to basically only one topology, unless you want to go to some non-housed of non-T0, no whatever, which I don't want. So and then you take the product topology. So there is this projection from sigma lambda to lambda, and then we prove that this map is continuous. And here, if you work with the lossy maps only, then using some very clever machinery, you can prove very easily that it's continuous. It was done by Ishii, and he also, I think, thanks Milnor for some ideas, and these are just nice formulas, but they are because the maps are linear. Here we don't have linearity, so we have to do it in a more complicated way. Okay, so we have those points where our attractor intersects the divider, and we call them gluing points. And then we have their images. So their images, first, second, and so on, are the points where you see that the direction of this unstable manifold changes. And we call them, the first image of the gluing point is the turning point, and further images are post-turning points. And what are kneading sequences? You take all turning points and find itineraries of those points. For the tent map, for example, or for the quadratic map and unimodal map, you have just one kneading sequence because you have one turning point. Here we have countably many turning points. But basically all the important information about this attractor is coded into the set of turning points. So each turning point is countably many signs and countably many turning points, so this is countably many bits of information. But it's organized in a kind of complicated way. So you have those two-sided sequences and infinitely many of them. So can you do something better? So you look at those basic points, G, T, and T hat, so gluing, turning, post-turning. And then it's not so difficult to prove that this set is discrete. If you take this, if you think about your lambda, in fact not lambda but the unstable manifold, because lambda is closure of this unstable manifold. So if you take this and straighten up, you have the real line and you have those points to the left or right. So, okay, so I told you about kneading sequences, but also you can just look at those points and mark which of those points are gluing points, which are turning or post-turn. So you get such a by infinite sequence. And here you put X just to that you know where your fixed point is on this real line of this manifold. So you have one sequence, which is also countably many pieces of information, but it's just one sequence, so it's much simpler. And we call this folding pattern. And if you want, you can think about it as some countable Markov chain, subshift of finite type with countably many states, because you have those intervals between 2 points G or T, and they are mapped somewhere, and they cover exactly several of those intervals. So you get such a tree, and you can mark whether it's on the right or whether it's on the left of X, and how far. So you have those numbers, but you see that those numbers are kind of in obvious order. So you can skip those numbers and still you have nice tree, and this tree contains all the information. So this theorem tells us that those three things, set of needing sequences, the folding pattern, and the folding tree, they contain the same information about the attractor. And this is information which a priori can give you everything like entropy or whatever you want. Of course, the problem is, one problem is whether if you have, say, two lossy-like maps, you have those needing sequences or whatever for one and for the other, and they are different, but maybe they are conjugate. Because we were identifying those turning points or the gluing points using the structure, the fine structure of our lossy-like map. So knowing where the divider is. But if you have conjugacy between two lossy-like maps, how do you know that turning points go to the turning points? Can you define turning points in terms of via purely topological terms? And the answer is very simple, no, because you can conjugate your lossy-like map with itself using itself. And then the turning points will be mapped by this conjugacy to their images. Post-turning points, not turning points. But now the question, so the real question is, can you identify using purely topological terms trajectories of the turning points? Okay, and I think this is all. Thank you.
On this folding tree, is the left-right order of the way those things branch, is that important?
Yes. Order is very important. I even write in the order of the vertices. You have to know the levels and order. If you switch, you get something different.
How can a point have two different itineraries?
Sorry?
How can a point on the attractor have two different itineraries? I think that's what you said.
What do you mean two different? One point?
Yeah.
Okay. Formally, yes, because if it's a gluing point, it's on the divider, then it's both on the right and the left. But this is the usual thing. In one dimension you have the same. The turning point is both on the right and on the left. So here you solve it by introducing new symbol, C, say, usually, but sometimes you don't. You just take the closure in the space of sequences.